A Boeing 747, weighing around 400 tons, needs a concrete runway several meters thick just to take off. Yet a freight train, weighing 25 times more, stands and moves on nothing more than a layer of loose, unbonded stones. No glue, no steel mesh, no cement, just rock millions of sharp-edged stones stacked loosely together. How can something that looks so chaotic and unstable support thousands of tons of moving steel at speeds exceeding 100 kilometers per hour without collapsing? If you look down from above, the railway appears unremarkable steel rails resting on wooden or concrete sleepers, all laid atop a gray bed of crushed stone. But zoom into the scale of centimeters, and you enter a strange physical world, one where disorder creates order. And microscopic motion is what keeps massive structures stable. Each stone acts like a tiny warrior, bearing pressure from thousands of directions. It does not crack or slide away. Instead, it locks tightly with its neighbors. These stones are never truly still. They shift microscopically, constantly rebalancing forces. Paradoxically, it is this continuous motion that creates the stillness we observe. As with many paradoxes in physics, the answer to why loose stones can be stronger than concrete lies not in weight, but in geometry, friction, and the nonlinear behavior of matter. If you have ever held a handful of smooth pebbles and a handful of sharp-edged gravel, you already understand the fundamental difference between rolling and locking. Rounded stones like river pebbles slide easily past one another. Under load, they move as a whole, causing rapid settlement and sinking. Angular stones such as granite or quartzite possess fractured edges, inclined faces, and sharp corners. Together, they form a cross-locking geometric system. When force from train wheels travels downward, the stones are not merely compressed, they are pushed sideways, wedged together, and mechanically locked, much like millions of microscopic gears engaging at once. In physics, this is known as an interlocking friction network. Each stone simultaneously acts as a load-bearing unit, a joint, and a mechanical stop. Static friction between rough surfaces can reach hundreds of kilopascals, far greater than dynamic friction. As a result, even without cement, the entire ballast layer behaves like a semi-elastic solid. More remarkable still, this elasticity is self-adaptive. As pressure increases, some stones fracture microscopically, creating fresh surfaces that immediately relock. The structure is continuously renewed, a form of self-healing unique to granular materials. This is why railway engineers strictly prohibit the use of rounded gravel. The sharper the stone, the stronger the interlock.
Look
Randomness
at the
in shape
uniformity
becomes
here.
an
It's clearly
advantage.
failing.
No two stones are identical.
I'm adding a priority
And this
flag to
very
this data
irregularity
point.
prevents the system from failing all at once. A chaotic system, yet irrationally stable. As a train moves, each wheel generates not only downward force, but vibrations that travel along the rails, a mechanical earthquake propagating into the ground. If rails rested on a perfectly rigid foundation like solid concrete, these vibrations would reflect back, creating metal fatigue through resonance, eventually cracking rails within years. Ballast behaves differently. Imagine this: as force travels downward, stones shift microscopically, mere thousandths of a millimeter, sliding slightly before stopping due to friction. In each tiny movement, vibrational energy is converted into heat and micro-deformation, like millions of shock absorbers working in parallel. This is a non-linear system. Its response is not proportional to the applied force. Small vibrations produce almost no reaction. Large shocks awaken the friction network, locking stones together and dissipating energy. The result is a structure that behaves like a smart material, rigid when load-bearing is required, soft when shock absorption is needed. Experiments by Deutsche Bahn show that ballast layers can absorb up to 60% of vibrational energy in the 2100 Hz range, the exact frequency band, produced by train wheels on rails. If concrete is a wall that reflects force, ballast is a cushion that listens. It does not resist vibrations. It consumes them. This is what makes the extraordinary possible a 10,000 ton train gliding smoothly atop millions of stones that know exactly how much to move. During heavy rain, you may notice water disappearing through the ballast almost instantly. This reveals another critical function, hydraulic regulation. In geotechnical engineering, water is a silent enemy. When water saturates soil beneath a foundation, it can trigger liquefaction, where soil loses internal friction and behaves like a liquid. Even a small disturbance can cause catastrophic collapse. Ballast acts as an inverse permeable membrane. It allows water to pass through immediately, retains fine soil beneath, and creates air channels that help the ground dry quickly after rain. The stones form millions of interconnected voids, an open graded aggregate structure. Tests by Swiss Federal Railways show that a 30 centimeter ballast layer can drain up to 1,000 liters of water per minute per square meter, hundreds of times faster than compacted soil. Because these voids remain open, ballast also stabilizes temperature by allowing airflow, reducing thermal expansion in rails. From above, a railway looks like a straight line. From below, it is an open circulatory system where water, air, and force flow in balance. An artificial circulation network, closely mimicking biological equilibrium in the human body. In dense forests where plants grow through every crack, railway tracks remain strangely barren. No grass, no moss, no roots. This is not luck, it is physical hostility. For a seed to germinate, it needs stable moisture, nutrients, and a surface to anchor roots. Ballast removes all three. Sharp stones generate extreme contact pressure. Young roots are crushed as they attempt to penetrate. Water drains too quickly to sustain moisture. Direct sunlight can raise surface temperatures to 60 degrees Celsius, a true microscopic desert. Continuous vibration from passing trains keeps the ballast in constant micromotion. Even roots that manage to anchor are gradually severed by friction. The result is a biotic void, a naturally sterile environment requiring no chemicals. In the 19th century, before herbicides existed, this physical sterility allowed railways to operate safely without biological invasion. It is a form of naturalized design, anti-biological by structure, elegant in its inversion of nature. If we simulate the motion of millions of stones in a computer, the outcome is never the same. Every collision, every friction point, every deformation creates unpredictability. Yet this chaos is precisely the key to durability. In a random system, there is no dominant weak point. No single stone bears the full load. When one fractures, force instantly redistributes, much like how forests recover after fires. This is the essence of an adaptive, nonlinear system, a model shared by both biology and advanced engineering. It relies not on perfection of components, but on the system's ability to self-organize and maintain balance. Ballast does not fight gravity, it negotiates with it. It does not resist vibration, it absorbs it. It does not preserve form, it continuously changes to protect what lies above. When concrete cracks, it fails. When stone shifts, it recovers. This is a lesson nature has long taught humanity. Flexibility is the highest form of stability. In modern engineering, we worship precision, rigidity, and smoothness. Yet sometimes, roughness and disorder form the strongest foundation of all. Each time a train passes, millions of stones beneath it shift, vibrate, and settle again. No stone tries to remain still, yet the system stands firm. True resilience, it turns out, is not about resisting pressure, but about absorbing it without breaking. Just like people, we endure not by avoiding change, but by adapting to it.